Hi everyone, this is Dr. G. Ravindranath Reddy working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So as we know that we are discussing the numerical methods and integral transform course. In that course, we are discussing about the Laplace transform. Now in this video, we are going to evaluate the integrals using this Laplace transform. Now we'll see how to use the definition of Laplace transform in order to evaluate these integrals here. So whatever the integrals we are going to discuss here, that integrals are improper integrals. So that improper integrals we are going to evaluate by taking the help of the definition of Laplace transform here. So we are having different kinds of improper integrals. One type is integrals minus infinity to infinity. So that is both lower and upper limits are in terms of infinity. Then this is also one kind of improper integral. And the second kind is when the integral 0 to infinity, only the upper limit is in terms of infinity, then this is also one kind of improper integral. And the next kind is whenever the lower limit is infinity, so minus infinity to 0, so this is also another kind of improper integrals. So out of all these types of improper integrals, you are going to evaluate the second kind of improper integral, that is whose limits are 0 to infinity, that is lower limit is 0 and the upper limit is infinity. Whenever for this type of integrals, we can take the help of this Laplace transform and we can evaluate that improper integrals using Laplace transform. So now, as we said, so Laplace transform can be used to evaluate the certain types of definite integrals whose integrals related to the improper integrals. That improper integrals are whose limits are lower limit is 0 and the upper limit is infinity, and then some function. So this we can also take the help of this Laplace transform to evaluate this type of improper integrals here. So I will explain the procedure here by taking one example, how to compare the Laplace transform definition with the given definite integral here. So using Laplace transform, evaluate integral 0 to infinity. So these limits integrals are fixed, that is 0 and the upper limit is infinity. And we can take the function here and dt. Now our task is how to evaluate this improper integral using the Laplace transform technique. Okay, now we'll see how to use this Laplace transform to evaluate this definite integral here. Now take the definition of Laplace transform. So what is our definition here? L of f of t is equal to integral 0 to infinity e power minus st into f of t dt. This is our definition. So 0 to infinity integral e power minus st into f of t dt, we can consider this integral as Laplace transform of f of t. Now whatever the integral he has given in the problem, you compare that integral with this standard integral. So the given integral is, this is our given integral in the problem, integral 0 to infinity t into e power minus 2t into sin t dt. You compare this integral with the standard integral. This is our standard integral and get the value of s value and f of t value here. So by comparing this, you will get s is equal to 2. So the power of this exponential compare this in the power, take the coefficient of t excluding that minus. So the power s is in place of s, here you are having 2, so we can take s is equal to 2. And f of t, what is neglect this exponential function. So neglect this exponential function here, and whatever the function we are having, the remaining function, you consider that remaining function as f of t. So here f of t is equal to t sin t. Now we'll see how to find out this integral value here. Now you compare, once again I will repeat, compare the given definite integral, improper integral, with our standard integral. This is our standard integral of Laplace transform. Now compare get the value of s and get the value of f of t. Now here you replace that f of t here. So now integral 0 to infinity t into e power minus 2t into sin t dt. So this we can take it as Laplace transform of t sin t. So here in the definition we are replacing that f of t with its value. Okay, so Laplace transform of f of t, that is in terms of s, but we know the value of s. So replace, after finding this Laplace transform of t sin t, we know the value of s. So replace that s value, s is equal to t. Okay, so now Laplace transform of sin t, t into sin t. So that can be written as, you find out this Laplace transform of t into sin t. So this is of the form Laplace transform of t into f of t. Use the formula. So Laplace transform of t into f of t, that can be written as minus d by ds of f bar of s. So that is equal to minus d by ds of f bar of s, that can be written as Laplace transform of f of t. So that is minus d by ds of Laplace transform of f of t is sin t. Or we have the standard formula. Apply this and continue this, find out the derivative. Otherwise, we have the Laplace transform of t into sin at. We have derived this formula in the previous videos. That value can be written as 2as by s square plus a square whole square. Now compare this Laplace transform of t into sin t. So here t can be written as 1 into t. So here we can take a is equal to 1. You will get 2s by s square plus 1 whole square. Directly we can use this formula, or we can use this Laplace transform of t into f of t. So this is very simple if you remember this formula here. So that value we have taken 2s by s square plus 1 whole square. Now here wherever we are having s, we have to replace that s with 2. So now simplify this. So use this formula. We have used this formula, t into sin at, 2as by s square plus a square whole square. So by taking a is equal to 1, we get this value here. So replace s is equal to 2. So simplify this, you will get 4 by 25. So this very simple. We are not using any integral formulas here. So directly we are taking the help of Laplace transform definition and then find out the Laplace transform of f of t. And in that Laplace transform of f of t, after finding that, you will get that value in terms of s. We'll replace that s value here. Finally, you will get our definite integral value. That is 4 by 25. Now let us take one more problem here. This value, integral of this. Same definition. Use this definition. Now find out this integral 0 to infinity. So here the difference between the previous problem and this problem is, in the previous problem we are having integral 0 to infinity e power minus 2t into f of t. But here we don't have the exponential function here. That is the difference between the previous problem and this problem. So here, in order to apply our definition of Laplace transform, along with this function must multiply with some exponential function here. So here we don't have that exponential function. So in order to get that exponential function, what I am doing is, I want to multiply this function with 1. So 1 into the same function. So now I want to convert that 1 in the form of exponential function, that is e power 0 into t. 0 into anything equal to 0. E power minus 0 or e power 0, that value we can consider as 1. So integral 0 to infinity e power minus 0 into t and this function. So now you compare this integral 0 to infinity e power minus st into f of t dt. So here why I have taken this problem is, So inside this integration, we don't have the exponential function here. So even though if any exponential function is missing in that integral, we can get that exponential function by multiplying the given function with 1 and convert that 1 in terms of exponential function. Then it will be converted into our standard form. So here by comparing this, we will get s is equal to 0. In place of s here we are having 0, and you consider this remaining function as f of t here. So f of t is equal to cos at minus cos bt by t, and s is equal to 0. Now find out the Laplace transform here. So now this is equal to, you consider this as equation 1. If you want to find out this integral value, just find out the Laplace transform of this numerator. So just find out the Laplace transform of this entire function, then replace s with 0. Now our task is finding the Laplace transform of this function. So once if you observe this one, this is of the form Laplace transform of f of t by t. So in the previous video we have seen formula for Laplace transform of f of t by t. So first we will concentrate this value, and then after getting that Laplace transform of this, in that replace s equal to 0, then we can get our required integral value here. So the next step, I am concentrating on this. So already we said that this is in the form of f of t by t. So that value has given as integral s to infinity f bar of s into ds. How can you get this f bar of s here? You compare this standard step formula with this and get the value of f of t. So f of t is equal to this value, and then apply the Laplace transform. You will get f bar of s is equal to Laplace transform of that numerator, cos at minus cos bt. This is our value here. Now apply this, replace this f bar of s in this, you will get this. Find out the integral value, s by s square plus a square minus s by s square plus b square. So you multiply the numerator and denominator with 2, you will get 1 by 2 of 2s by this minus 2s by this denominator. So this is of the form integral f dash of x by f of x. So this can be written as log f of x. So this we can convert as 1 by 2 into log of s square plus a square minus log of s square plus b square. So this is of the form log a minus log b, log a minus log b. So this can be written as log a by b, that is 1 by 2 into log of s square plus a square by s square plus b square between the limits s to infinity. Now if we substitute this s is equal to upper limit infinity in this function, then we don't get any value here. This value becomes undefined because you will get infinity, log infinity is undefined. So now to overcome this difficulty, what we are doing is, whatever the s we are having, I want to convert that s in the denominator here. Because why? Because so if you substitute s as it is, here you will get infinity. So now you convert that s in the denominator, so you will get 1 by infinity, so that can be written as 0. So in order to get, I want to get this s square common from the numerator and denominator. So if you take s square common here, s square by s square, you get to denominator and denominator s square gets cancelled. You will get 1 by a square by s square, denominator 1 by b square by s square. Now if you replace s is equal to infinity in the denominator, 1 by infinity is 0. We can get some log value here. So in order to get that log value of, if you substitute the upper limit, I want to take that s square common from the numerator and denominator here. So now this becomes 1. So this becomes 0 because 1 by infinity is 0. This also becomes 0. 1 by infinity is 0. So 1 plus 0 by 1 plus 0, that is 1. 1 by 1, that is log 1. Now you substitute this lower limit s as it is. There is no change in the function. By replacing s with s, you will get the same function here. And we know that log 1 is equal to 0. So 0 minus this you will get 1 by 2 minus this. So if you want to remove this minus sign here, you just reciprocal this numerator and denominator. Write it as numerator, write it as denominator, denominator, write it as numerator, so we can cancel this negative sign. So this is our final value here. Not final, this is the value of cos Laplace transform of cos AT minus cos BT by T. So this is our f bar of s value here. Now after finding that f bar of s, replace that f bar of s, we got this value. Now you substitute this value here, this. So from 1 we will get this value is equal to this. We got this value is equal to this is the value of this. Now in this you substitute s is equal to 0. If you substitute s is equal to 0 here, you will get 0 plus b square, that is b square, 0 plus a square, that is a square. So in the both b square and a square we are having square common, so we can take log of b by a whole square. Now send this here, power of that, you will get 1 by 2 into log of b by a. This 2 gets cancelled, you will get log b by a. This is our final value here. So by using this technique, Laplace transform definition, we can evaluate the improper integrals whose limits are lower limit as 0 and the upper limit as infinity. This type of improper integrals we can evaluate by taking the help of Laplace transform. Now in the next video, we will go for the Laplace transform of periodic functions. So in that we will discuss what is meant by a periodic function, definition for periodic function, and we will derive the formula for Laplace transform of such periodic functions, and we will take some examples here. Thank you.